So, thank you for coming, and it has been decided that English should be the normal language. I will speak English my own way, and I'll begin immediately by putting some words on the blackboard in order to explain what I want to do. I will divide the blackboard in two parts. One part will be philosophy, if you like it, or concepts. Mathematicians are not working with concepts. That's not their ways of doing it. They are working with theorems, properties, theories, and so on, figures, but not concepts. So the first concept I will use is a concept invented by Auguste Comte, analytical fact. I think I've never seen it before. Le fait analytique. It is obviously not in Kant, and it is which is something completely different. And it is not well. It is in Auguste Comte. It is second lesson, the cours de philosophie positive, 1930. For analytic fact, I will in fact use Comte, and it's I put the date. But Gaston Bachelard, who did this thesis, his second thesis on the propagation of heat in 1929, discussed Comte analytical facts and explains something of he says something which is amusing in a way. He said there is a first degree of analytical fact, that is Comte, young boy, and there is a second degree of analytical fact, Bachelard, who has very well understood Comte and so on and so on. So I would put Bachelard. It's very clever what he says, but a little bit. So 1929. Now my second thing will be, I'll put it in a very simple way, structural property. Well, it is structuralism which is involved, but I'll give some dates perhaps. So notion of Hilbert space. Well, I will use a date, something rather late. That is the day when John von Neumann, so I won't write John von Neumann, but John von Neumann wrote Grundlagen, mathematische Grundlagen der Quantummechanik. And that's where he defined the word or the expression Hilbert space. So that was in 1932, and well, this will be perhaps enough. Now I will use something which is very well known, the notion of epistemological obstacle. I'm not sure this is the standard translation of Bachelard, l'obstacle épistémologique. I don't know what is standardized in English, but I think it's something Bachelard. So it appeared really in 1940, Formation des spécifiques. Now I will use something which perhaps is not a concept, but description, computational technique, the technology would be. So I will use, you'll see why, Heidegger, and in, let's say in the 50s, to Rabelais. And perhaps something surprising, I will use Darboux as the editor of Fourier works in 1890. So I'm mixing a little bit of things. Now, this is one thing. Now, I will use in front, let me say in front, in fact, only one relation, one inequality. Well, I will use the Heisenberg relation. This will be my way of discussing about the rules, so my way of storytelling the world facts. Now, the problem is how to write Heisenberg relation. I will write it in a way which was impossible up to, let's say, 2000. Before, a mathematician, and for sure a physicist, will never have written like that. But I will write it in a way where you can see why it is related to Heisenberg relation as they were written in 29 for the first time by Heisenberg. So I'll write it, perhaps if I can put it, well, one way is, that's the easiest way. So I'm taking an integral over the rule R, and I take the function f. We'll have to discuss about this. Well, I put modulus n squared power 2 dx. This is one part. And I do exactly the same for another part, which is a Fourier transform. I will define or explain what it is, but I don't want to write formulas about the Fourier transform first. So there is something, think of, there is a transformation of f, which can be transformation, and we are now used to say, which is rather recent in a way, to use f hat for the Fourier transform, and so you have exactly the same. So I'll put the variable for the Fourier transform in terms of C. So you see why. So the same thing, m to power 2, and then, okay. Now, what is the Heisenberg so-called relation is, there is something here. This product, technical product, is universally greater than a constant. That is, there is something, I can give you the true value, but who cares? It's 1 over 16 pi over 2, so you can, if you want to be a poet, discuss of the appearance of pi because of particles. French. But I mean, there is something which says that, well, this is what I want to explain. This could be considered as an analytical fact. Oh, I forgot to say, xm is just the middle of function f. You may understand, you have function f on R, well, you may think there is a middle point. Same equals this. Power 2, you will understand, it is because of Hilbert space. Now, this relation, universal. First point is, this may be considered as an analytical fact. That is something which you can prove from a certain number of facts, for sure, but which can prove without thinking of any physical or even mathematical interpretation. You do it formally, you have this, and this. Now, this is a way of saying.
So is there an integral in the parentheses?
Oh, sorry, sure. But I began with same. Oh, sure. Thanks. Second thing, which is to be said, you can say that this analytical fact is just the fact that there exists a cosine. You may consider that this here is just something like nothing more. Or if you want to have a little...
The first is equivalent to the second?
The word equivalent is right if you are in a Hilbert space, that is, if you put in the structural property. Analytically, no. Because you have to have an interpretation. an interpretation of your structure, a geometrical interpretation. So that's the reason why I say this is, I didn't say equivalent, this is the interpretation in geometry, but this is not exactly the same, it depends. What I want to say is this is not an analytical fact, except if you say, oh, it's a geometrical fact, but not an analytical. Yes, the geometrical fact is that.
Of the definition of the cosine.
Forget about cosine, say projection. Yeah. And you have projection in any kind of geometry. Not so this means that is always less than that. Was that your answer? If not, you are lost. Now, this is a second way. But a third way of explaining is by computational technique. You can completely describe this. And this was what was done around 2000 to say that this is the way F is being, that is a standard deviation of a representation on the real axis. Standard deviation, which is usual, let's say, improbability for sure, but description, you have a phenomenon, a quantitative phenomenon, and it has a middle point, and it is around this middle point in a certain way. So what you write here is, if you have the standard deviation, let's say, of F, you multiply, this is the same, by the standard deviation of F hat. This is always greater than something constant and universal, which means if you know F around a certain value, you cannot know up to a certain error, let's say, you cannot know F hat around the equivalent value with the same way. You think of Heisenberg immediately in a physical point of view, but I don't speak of moment, speed, position, not at all. We are in the old world was pure mathematics. That means something coming from nowhere, except that this interpretation could not be given without the help of computers and computational techniques. It is because during the 20th century, lots of people tried hard to raise computational ability to compute the Fourier transform, but they lost. The fast Fourier transform is a good technical way, but it failed. That is, you cannot go up to a certain point. And this was not a priori. It took 30 years, plus computational techniques, computers, to discover that there was a limit, and to discover that this limit was due to this, explained in that way. So, I don't want to go too much. It is, when you think of this computational technique, in pure mathematics, it was because of an impossibility, which was not easy to discover, that you have an interpretation. It is because of technique that you have a critical interpretation. Critical in the philosophical sense. A critical appraisal, if you like, of this which was known. So think of it. This is more or less, my interpretation is, now, and this is my main point, to obtain not to think of it. But to obtain that could have been done by Fourier. The technology, the mathematical technology, doesn't depend on Hilbert space, doesn't depend on Fourier could, I say could, but has not discovered it. So I won't prove it. It is easy. It is. I mean, within less than 1 page, you can prove it. You have a little bit of some techniques about Fourier transform, but it is easy. Now, once it is said, you see that in a way I am answering. I am using the notion of epistemological obstacle. I will use it a little bit further. But here, you cannot say that the non-discovery of that, or the non-interpretation, is because there was an epistemological, there was something in theory, something which, or your mind was prevented from. On the contrary, you may say that the technology used by Fourier, if I use the word technology for his own computations, the technology of Fourier was to think in terms of not something of that sort, but on the contrary of a splendid dictionary between F and F hat. What is a splendid dictionary for a mathematician? It is when you know that you have a certain function F belonging to a certain space, a certain group, having a certain number of properties. And you have a representation of F hat so that you have a bijection, and you must, well, bijection, that's not enough. You must have a continuity behind. This problem of bijection continuity were solved only in the 20th century. Two examples. What is called the L2 method, that is structural property of Hilbert space, but not, you cannot have only Hilbert space. You must have something related to what a function is. That a function, it takes values at certain points. So the L2 gave a perfect bijection. You may say this was done by Plancherel in 1910. Or it's older than. Now you can have another way, which is perhaps we shouldn't forget about it, is distribution theory, Schwarz theory. Perfect bijection. It was done before. Yes, but you can go and look at Schwarz. This is never written, never thought. Now, so that the epistemological obstacle can work. But also, this is not the way. This was found, this analytical fact. Now I have to go quickly in the following way. Well, to go back a little bit to where it comes from. That is where the Fourier transform was raised, invented, and so on. And now we have a nice epistemological and historical problem. So I will tell one story first, and then a second story. First story is easy. It's Fourier case. Wonderful thing with a word. He is speaking of propagation of heat. He has obtained, this is difficult, rather difficult, but he has obtained an equation. That is, he has obtained that when everything is nice, that is, time doesn't intervene for propagation of heat, that is, when there is an equilibrium, he has shown that the temperature in a surface, in a volume, and so on, the Laplace, oh, it's not the same delta. I put it like that, double delta. The Laplacian of T is equal, temperature is 0. Okay, nice. There must be, okay. Now it takes an example. Well, an example, usually, Comte says so. The example, he says, is an experiment. But Comte and some others never had the idea of thinking in terms of Denk experiment, a thought experiment. So what is the thought experiment of Fourier? It is, you take a metal lamina and you cold it, that is 0 degree. There is no source of heat at infinity, nor something which takes your heat like that. You have just propagation. Now, and you have a function f. Heat is here. Some heat. Yes. And the question is, what is the value of T here? And the answer of Fourier is, I can compute it, but how? By thinking of the existence of proper mode. I am not inventing the word. Le mode propre. Even you put it in the plural. Which is a proper mode. But for us it is clear. It is just a proper vector in a linear space for a certain linear operator. And the modes are given the proper values. Yes, but Fourier is the one who invents the word and the idea. That is, he claims that if there are certain function f, when you put them here as temperature, any function, this is not an experiment you can do physically. Well, certain functions are such that if you take at a higher level, here, you have to think in terms of level because of the symmetry of the apparatus you're working with. Then the idea is, here, the temperature will be F, lambda F. Not a constant. It cannot be a constant. It has to be the following thing. Here is a function depending on this variable, let's say f of x. Here it will be f of x plus lambda, a constant, depending on the a. So you're looking, now, in our turn, you are looking from the proper vectors of the Laplacian operator in a given geometry. You must have a geometry. That is, you cannot reduce this to just one variable. It is because heat is going at least in a surface that can work. The mode we define as a sinus and cosine. Fourier didn't like complex numbers and complex exponentials. He worked on this. Now, he has obtained something which, look at the word proper mode. He has hesitated clearly by saying natural mode, then proper mode. And proper is far better. Which is to say that this does not depend on your geometry, on the initial values, and so on. There exists, in any surface, in any volume, proper modes. Second question, they are enough to represent the whole system. That is, you can now solve your problem of heat propagation. I won't go into that point. My main thing is there is something which is purely dependent on the geometry. You say, and that Comte is clever about it, it's a thermal geometry. putting geometry, something which is in our mind, and something thermal, something you can feel, you can perceive together. Well, this is a definition also in a way of mathematical physics, but you see how it is obtained. Now, quickly about the end of that. As once you obtain that, you can now think in terms of analysis. So, have I obtained really the rule theory? That is, shall I learn more from this geometry I've invented? And there is a beautiful part of the Fourier's book is that it takes different kind of a cylinder, a sphere, a cone. The worst is a tetrahedron. Try to do the calculation of a tetrahedron. It's awful. Okay. But the question is, I'm not interested in heat diffusion on the tetrahedron. What I want to know is my analysis exhaustive? And it is at the end, after 20 years of work by Fourier, in 1822, that he discovered that he had forgotten one thing, which for us seems astonishing: the rule plane. And if you don't have a limitation with a geometrical object, you take the plane, and you take just a line. Just a line with heat, and you look temperature there. That's where he invented Fourier transform, integral Fourier transform. It's for us, it's strange. He should have thought, if this has a meaning, by the way, but he should have thought first without geometric limitation. And he couldn't. And this was, in fact, the idea came from Cauchy. It is clear when you look at history. There is no problem.
In the first version of the book is not considering the diffusion of the black.
Lamina.
Lamina. Yes, but so you may make the limit here make an essential difference.
It came in his manuscript. It came around 1817, never before. And for an analytic mind like Fourier, it's wonderful, but think of it. I mean, in 1822, he has discovered, and immediately, the properties he had obtained for the limited Fourier transform, which is for periodic functions, to speak in a more mathematical term, the Fourier transform he had obtained by analogy without any computation gives him the translation in terms of Fourier transform. The inversion of the Fourier transform for Fourier is obvious. Obvious means there is a theory with periodic function. I can go to the R number. Afterwards, you will put all what you want as a rigor analysis. You know that you have something. When you obtain a thing like that, you cannot think of something like that. I mean, you have obtained something which seems completely described. The minor point is, if now, okay, I have my proper modes, but can I obtain any function? Yes. There is a mistake in Fourier's mind, but this was a mistake of the time. Any function is integrable, which takes a bounded function. It's no problem. Well, in order to have this result, the structural result, you have to restrict. You have to restrict. You have to have not integral in the usual sense. You have to take Lebesgue integral, and it doesn't work if you still remain integral with Riemann integral. It is, you know. But and you can put the rule theory of Fourier in good setting, but you cannot think that there is a limitation. And where Fourier is within this difficult thing, I'd say, but analytical fact, the analytical fact for Fourier's time was, how is it possible that when you have any periodic function, any, or something like, so I do a drawing which is today absolutely common among engineers. You have a periodic function of that K, of that phi. Or you can do that. Or you can do what you like. I mean, and something which is a usual trick in electronic to have. Now, how can this be represented by sines and cosines? And the answer was impossible. Nature has a possibility of having sine and cosine, proper modes, which are natural, and nature also can have this kind of representation. Well, you know, it's the same if you do the analogy. Take a violin. Take a string of a violin. I can do pizzicati. How anybody may think that pizzicati are harmonics. You are not authorized to do that when you are playing violin, except now, this was the problem. The real analytical fact was for Fourier to claim that any function, that's almost nothing here, can be expressed by periodicity. And there was a problem. There was a problem, that is, if you want to have periodicity, and if you want to have sinus, you will have a problem of that kind. Here it goes high, or here it goes down. This is not uniformly convergent, that's it. Now, and I finish here. The analytical fact for Fourier was a representation of periodical function by harmonics, with no limitation on f. This was too strange, too far away from his fiction. The interpretation which I tried to give were clever among a certain number of things concerning Fourier, but doesn't give us the status of Fourier transforms nowadays. This status, and this is my summary of it, you have to change your epistemological description and values according to the way science is evolving, and this gives you, because you do that, a better, at least more concise, more precise appraisal of what was done before. We see Fourier in a far better way nowadays than we saw it even, let's say, 20 years ago. That's what I wanted to, with almost no question.